Have you ever looked up at the night sky and wondered, where did all this come from? Not just the stars or planets, but everything. The galaxies, the empty space between them, even time itself. In this lesson, we're going to rewind the universe. We'll explore how it all began, how tiny ripples turned into colossal galaxy clusters, and why some of what we see doesn't quite add up. As we journey through space and time, you'll discover not just what we know about the universe, but what we're still trying to figure out. Ready to go back to the beginning? Before the first star ignited, before the first atom formed, before space and time as we know them even existed, what did exist? Anything? Was there a universe at all? Scientists actually aren't sure. But what they do know is that about 13.8 billion years ago, everything in the universe was packed into a point smaller than a single atom. Then, in a moment called the Big Bang, the universe began rapidly expanding. It wasn't an explosion in space, it was the rapid expansion of space itself. Time began ticking. Matter and energy burst into existence. We don't yet know exactly why the Big Bang happened, but physicists believe it may have resulted from tiny energy fluctuations, possibly linked to the laws of quantum mechanics and gravity. It's one of the biggest unanswered questions in cosmology today, and the topic of much ongoing research. In the first tiny fraction of a second after the Big Bang, the universe underwent a phase called cosmic inflation, growing unimaginably fast. The matter that had previously been squished into that single point began spreading out across the growing universe. The universe had now become a hot, dense soup of particles, specifically quarks, electrons, and photons. But let's pause here and review just a bit of chemistry so that this makes sense. We know that atoms are made of protons and neutrons, which form the nucleus of the atom, and electrons, which occupy the space around the nucleus. But protons and neutrons can be broken down into smaller particles known as quarks. So the quarks are already in existence at this early point of the universe, and they soon begin to combine, forming protons and neutrons. Within several minutes, the protons and neutrons began joining together to form atomic nuclei in a process known as nucleosynthesis. Can you guess which elements formed first? The simplest and most common ones, hydrogen and helium. Although at this point hydrogen and helium existed only as bare nuclei because electrons hadn't cooled down enough to link up and create whole atoms. But there is one more particle in existence already. Photons. Remember that photons are particles of light. And while its particles were already in existence, light still couldn't travel freely. It kept bouncing off the newly formed nuclei in the dense plasma soup. It was like trying to shine a flashlight through thick fog. This fog lasted for hundreds of thousands of years. Finally, around 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with nuclei to form atoms. This moment is known as recombination. With the protons, neutrons, and electrons now organized into stable atoms, the dense fog that had permeated the universe became more transparent. Why is this important? For the first time since the universe's formation, light could now travel freely. That ancient first light, still traveling today, is called the cosmic microwave background, and it's one of the biggest clues we have about the early universe. The cosmic microwave background radiation, or just CMB, can be thought of as the universe's baby picture. A snapshot of the cosmos when it was just a few 100,000 years old, and the very first light was beginning to travel freely across the universe. It's not visible to our eyes, but special microwave telescopes can pick it up as faint radiation coming from all directions in space. Using increasingly improving technology since the 1960s, scientists have been able to use these telescopes to map out the distribution of this early light across the universe. What have they learned? First, it's everywhere. No matter where we look, we see this faint glow, almost perfectly uniform. The key word here being almost. Zoom in close enough and you'll notice tiny variations, slight changes in temperature and density, like faint freckles on an otherwise smooth face. These tiny fluctuations are important. They represent the earliest signs of unevenness in the universe, areas where matter was just a little more concentrated than others. Though tiny, these differences would have powerful consequences over time. Think back to what you know about the formation of our own solar system. In its early days, what resulted from the pockets of uneven mass like grains of sand and rock? Eventually, they clumped together to form planets. Now take a look at the uneven spots in the cosmic microwave background, or CMB. Pause the video and make a prediction. What do you think those tiny differences in the CMB eventually turned into? These early variations, the small differences in mass, would grow into the complex structures we see in the universe today, like stars, galaxies, and galaxy clusters. Let's take a closer look at that process. After the cosmic microwave background was released, the universe continued to expand and cool. But it wasn't perfectly smooth. Remember those tiny fluctuations in the CMB? In some places, there was just a little more matter than average, and that made all the difference. In these slightly denser regions, gravity began to do its work. Even small clumps of matter started attracting more material from their surroundings. Over millions of years, those clumps grew. As they grew, the additional mass caused them to become more dense and compact. The denser the region, the faster it attracted more matter, forming larger and denser clouds of gas. When a large amount of matter becomes very dense due to increasing pressure, what happens to temperature? It increases. Eventually, some of these gas clouds became so dense and hot that nuclear fusion ignited within them, forming the first stars. These stars grouped together into galaxies as gravity drew them together, and galaxies gathered into clusters and superclusters for the same reason, forming a vast cosmic web that stretches across the universe. So galaxies aren't scattered randomly, but instead form clusters and superclusters separated by enormous voids. It all traces back to those tiny irregularities in the distribution of mass in the early universe. Stars within these galaxies continued forming, living, and dying over billions of years, creating heavier elements in their cores as they did. These elements went on to seed the formation of other stars and planets across every galaxy in the continually expanding universe. And so the story continued. After about 10 billion years, on the quiet edge of a spiral arm of the Milky Way galaxy, this process gave rise to a particular but average star. In another 4 billion years or so, that star would become known as the Sun by the inhabitants of a planet that formed around it, Earth. As scientists study the structure of the universe, they notice something strange, something that didn't quite fit. Based on everything we know about gravity and the amount of visible matter in the universe, galaxies shouldn't have formed as quickly or as sturdily as they did. Galaxies spin at such high speeds that if they were held together only by the gravity of their visible matter, they should be flying apart. But they're not. Even entire galaxy clusters, massive collections of hundreds or thousands of galaxies, seem to be held together by more gravity than we can account for. The same goes for the way light bends as it passes near these clusters, a phenomenon called gravitational lensing. The bending is too strong to be explained by the visible matter alone. So, where is all this extra gravity coming from? These puzzling observations, galaxies spinning too fast, galaxy clusters staying bound, light bending more than expected, sparked one of the biggest scientific mysteries of the last century. They suggested that something else must be lurking out there, something we can't see. But what? That question and its likely answer would vastly change our understanding of the universe. So what is the answer? Well, I hope you like a good cliffhanger, because I'm afraid I'm going to have to leave you with one today. It turns out that scientists do have a pretty good idea of what's behind the mystery here, and next time we'll dive in deeper to see what they've uncovered. But I'll give you a spoiler. It has to do with something called dark matter. And that brings us to the end of our journey through the formation of the universe. From a tiny hot speck to a vast cosmic web filled with stars and galaxies, we've explored how the universe took shape. But as we've seen over and over again, discovering answers to questions about the universe usually just leads to more questions. We'll continue our quest to answer them next time. Until then, keep marveling at the wonders of our universe.
Hey, hey!